Okay, so moving on to liquid mixtures. Okay, so I came up with an equation here earlier. Delta G of mixing equals nRT times chi A, natural log of chi A. So this is just kind of a good little quick review. Chi B times natural log of chi B. Okay. And we also wrote up this equation, delta S of mix, which we know is just negative ddt of this equation. So that's negative nR chi A, natural log chi A, plus chi B, natural log chi B. And we also remembered that when we combine these two things using the equation, delta G of mix equals delta H of mix minus T delta S of mix. This gave us that the delta H of mixture of an ideal solution is 0. All right? So what about ideal? So this is ideal mixing. Well, what about the ideal volume? So delta V of mixing, okay? So question mark. So as it turns out, look, the partial derivative of G with respect to P at constant T, hopefully you remember, is volume, right? So now if I want to talk about my volume mixture, so ideal volume, so delta V of mix is going to be the partial of delta G of mixing by the partial P at constant T. Okay? And if we were to do this derivative, we just get 0 for that whole thing because there is no pressure in here. So when temperature is a constant, well, look, R is a constant and N is a constant as well. So the whole thing just drops out to 0. So what does that mean to have 0 change in volume for ideal mixing? It's not quite what you think it means. It's a little counterintuitive, the derivatives, but once I draw you this picture, hopefully it'll be very intuitive. So suppose we mix two liquids together and they form an ideal solution. And let's suppose I've got 100 milliliters here and 100 milliliters here. Well, 4 years of a chemistry degree should tell you that it makes 200 milliliters. And if that's the case, then it is ideal. So what this delta V is really in reference to, does that delta V, is it any different than this, right? So let me see if I can write this a little bit less confusing. So V final minus V initial, right? And so our V final in this case would be 200 milliliters. Our V initial in this case would be 200 milliliters. So that would give us 0. Now, if we mix 100 mils and 100 mils, and we initially get 200 because we've added 100 and 100 together, but now the thermodynamic environment influences that volume to change relative than what we think it should, then we will no longer have a 0 value for delta V of mixing. And that also proves to us that it was not an ideal solution, okay? So delta H of mixing equals 0 makes an ideal solution. Delta V of mixing equals 0 makes an ideal solution. And the final one I want to talk about are the interactions, so the intermolecular forces between these things. So suppose we had A and B that I was mixing, okay? So now if we look at their interactions, or in other words, their intermolecular forces, right, the IMF, there are going to be interactions between an A and an A. So I'm going to draw that, and I know it looks like I'm saying a bond. Let's make it like a dotted line, dot, dot, dot. Maybe it's like a hydrogen bond or something, okay? So there's an interaction between an A and an A. there's an interaction between a B and a B. And then, of course, there's also going to be an interaction between an A and a B. Okay? And so for ideal solutions, all of these interactions will be equal. So I will say the average A to A INT for interaction is going to be roughly equal to the average interaction between B and B, which is going to be roughly equal to the average interaction between A and B. So for example, suppose all of these interactions are hydrogen bonds. So if A can hydrogen bond to another A, and B can hydrogen bond to another B, then we could conclude that A will likely hydrogen bond to a B, and thus all of those interactions will be roughly the same, and this would be ideal. Okay? So the solution becomes non-ideal, or a real solution, or an ideal dilute solution, however you want to think of it, if the following happens. So if the average A interaction is not at all similar to the average B interaction, which then of course would not be at all similar to the average AB interaction. So for example, suppose A is able to hydrogen bond with another A. Okay. But now suppose B cannot do any hydrogen bonding. So suppose it can only do London dispersion. Okay. So maybe an example of this is A is water and B is some greasy alkane, right? Well, then definitely they're not going to interact with each other, right? So the interactions all around are going to be different, and this makes a real solution, okay? And of course, that real solution we could further classify as ideal dilute if the solute follows Henry's law and the solvent follows Raoult's law, okay? What is my next slide? Okay, so continuing along, so I have one last little bit. I left myself one tiny little corner. So now we recognize that delta H of mixing equals 0 for ideal solutions. Well, for non-ideal solutions, there's two cases. There's when delta H of mix is greater than 0. So an endothermic solution. Endo solution, okay? And then, of course, there's delta H of mix being less than 0. So that's an exothermic solution, all right? And if we were doing like a live class discussion, I would break and we would say, let's talk about some examples of these. So you could pause the video and think about some of these examples for yourself. I'm just going to go ahead and tell you about some that I think are really cool. So the one, to me, the easiest one to think about for an endothermic solution is basically exactly what I just described, okay? When you have something aqueous and something fatty, for example, soup, like the stuff you eat, not chemistry, but like let's suppose we're making soup and we've got some water, but we've also maybe thrown a chicken carcass in there, right? We've got some fat that we're trying to extract. And so once we make that lovely soup, and suppose we pull out the chicken carcass and all the stuff and we've made ourselves, maybe not even soup, but just stock. Maybe we're just making soup stock, okay? So if you think about it, you have to heat that stuff up to get it to mix, right? I don't know a single person who's ever been able to make soup stock by not heating it up. So that's endothermic. You're adding heat to make the fat and the water mix. And then if you've ever taken that stock and put it in your refrigerator, you know that it then separates. It spontaneously separates, and it spontaneously separates because there is a required input of heat to make them mix. And so to get them to mix, you either have to actually do work on it, you actually have to mix them together. That's endothermic. You're providing work, you're doing work on the solution. Or you put it back in the pot and heat it up and make it mix, okay? So that's a really good example of an endothermic solution. Other examples of endothermic solutions are actually cold packs. One of the most popular cold packs is made up of ammonium nitrate. It's got ammonium nitrate crystals in it, and when you break it, there's a little pouch of water that dissolves those crystals. So you're mixing water and ammonium nitrate, and that actually requires an input of heat to get them to mix. And so those become cold packs because now if you, let's say, put it on your body, it's going to take heat from your body to get that thing to mix, to add the required heat to mix. So because it's taking heat from your body, it's going to feel cold. So that's how those cold packs work. Now, coming up with examples of exothermic solution formation is rather tricky. The best example I've got for you is sodium chloride, salty water. And that's because the interactions between sodium chloride and water are much different than the interaction between just sodium chloride and just water. Okay? Well, they're pretty similar actually, but there's a much stronger interaction between the water and the sodium chloride. And because that's such a favorable interaction, heat is released when you mix those things. Okay? So the last little